Prove by induction this summation formula. So I am first of all going to go with n equal to 1. And the left-hand side will equal simply, I'm going to be going from r equals 1 up to 1. So it's going to be 1 times 2 times 3, which is 6. And the right-hand side is a half times 1 times 2 squared times 3, which again becomes 6. So it's true. Let's assume that this summation formula is true for n equals k. And that means that the sum from r equals 1 to k is going to be a half k plus 1 squared, k plus 2. Now I want to show that this implies that it's true for n equals k plus 1. So it's good to write this down. This is what we're going to be aiming for, that the sum from r equals 1 to k plus 1 of the same summation is going to be a half k plus 1, k plus 2, k plus 1 plus 1 squared, and then k plus 3. That's what I'm trying to achieve. So let's start with it. The sum from r equals 1 to k plus 1 because it's going to be the sum from r equals 1 to k. And then I'm going to be adding on this extra term when r is k plus 1. The reason I've done this is that now I can use the result that we've assumed here. So I'm then going to get, I'm going to struggle to fit this in, I've realized. So it'll be k plus 1, k plus 2, 2, k plus 1 plus 1. Should be there. So then that will equal my assumed result, a half k, k plus 1 squared, k plus 2, plus this extra term. Which then becomes 2k plus 2 plus 1, so 2k plus 3. Remember, we're trying to get to here. So I'm going to factorize out a half, then k plus 1 and k plus 2. I've got this part. I can't factorize any more out because they're just not there, but I can factorize that out from both, in fact. That will leave me k times k plus 1 plus 2 lots of 2k plus 3. Then I'll get k squared plus k plus 4k plus 6. This just becomes 5k. And I won't do it all in one step, but we are there because this will factorize as k plus 2 times k plus 3, which does actually just become k plus 2 squared. In fact, I'm not going to write another line down. I'm just going to bring it together like that. Okay, which is, as required. So what this means is true for n equals 1 and n equals k true implies n equals k plus 1 true. So essentially, n equals 1 being true implies that n equals 2 is true, which implies that n equals 3 is true, and so on. And therefore, by the principle of mathematical induction, result is true. I should probably just say for all, what is it? For all positive integers n. Just bring this down while I'm at it. Okay. Hence show that for all positive integers n, the summation from r equals n to 2n is given by this. So this is going to equal the sum from r equals 1 to 2n of all that stuff, minus the sum from r equals 1 to, sorry, that's meant to be an r, up to n minus 1. Okay, because if I have 1 to 2n and I subtract 1 to n minus 1, I'll be left with n to 2n. So what I can do now is take the result that we've proven and just sub in for those two instances. Okay, I'm going to sub in n equal to 2n into this formula, and then n minus 1. So it'll be half times 2n times 2n plus 1 squared times 2n plus 2 minus a half n minus 1. N minus 1 plus 1, that's just going to become n squared, and then n plus 1. So what to do? Gonna factorize out. Now I can rewrite this as 2 lots of n plus 1 and cancel them out. And then I will factorize out a few terms. A half, first of all, because they have in the answer, n, because that is a common factor. And by cancelling this down, I can see that I've also got an n plus 1. Let's take out as much as we can. So that will actually leave me 4, because I'm taking a half out. I need to times by 2 on the inside. Lots of 2n plus 1 squared minus n minus 1. Okay, that's a good first step. Then I'm going to get 8. No, sorry, I'm doing this too quickly. Just 2n. Let's deal with the 2n squared. It'd be 4n squared plus 4n plus 1 minus n squared plus n. Then I'll get 16n squared, but I'm minusing n squared, so it'd be 15n squared. Then plus 16n, but I'm adding n, so it'd be plus 17n plus 4. Okay, and then I just need to factorize that second bracket. So I don't think it's going to be 15 and 1, because that would just be, I don't think it would work out. We could try it, 15n and n. We'd have to put a 1 there, but then you'd have to put a 4 there. It's going to be too big. So then our other option is to go with 5n and 3n. And then if I go with 4 here, I get 12, and 1 here, I get 5. That will all work out. If you can't see the factorization, then you can just use your, you know, it is worth being aware of. You can use the quadratic formula to get the roots, and then you can work your way back. I'll just show you in case you've never seen it. So we get roots of minus a third and minus 4/5. So it just gives plus a third and plus 4/5. But then we recognize we need a 15, so I need to basically times this one through by 3, give me the 3n plus 1, times this one through by 5, and we get the same answer. Okay, it's quite a useful little method for like when it's really complicated. But anyway, this is our final answer. Remember, it asked us to leave it in the form shown, which we have done. So this summation is equal to this. Well done.